Hello everyone. Today we're going to talk about more waves, and we're going to talk about some prerequisites to one of the most important topics in the whole course and the entire field of music information retrieval. This tool, the discrete Fourier transform, is the foundation of almost every analysis thing that we're going to do. So every algorithm where we're teaching the computer to listen to some aspect of music is going to use the discrete Fourier transform as the first step. And so I've got some cats here. They're ready to go. They're riding the wave. So let's ride the wave with the discrete Fourier transform. Okay. Now, I'm actually going to take you through a journey that I went through myself when I was younger. I did a high school science fair project trying to teach the computer how to listen to my violin. I had no idea what I was doing, and I hadn't even had calculus yet. But I did just have trigonometry, and that was actually just enough to understand this. And I just, by chance, the web was a bit earlier on. This was the early 2000s. I stumbled into a really good tutorial on the web about the discrete Fourier transform that only required trigonometry to understand. And so I'm going to take you through that and hopefully replicate some of the kind of aha moments that I had myself, which actually shaped my trajectory for the next almost 20 years at this point, because I've been doing this ever since. Okay, so hopefully some of you will catch this bug, this good bug, the DFT bug, the same way that I did. Okay, so the discrete Fourier transform DFT. Now, before I go through the DFT, I have to define something called the dot product. And this is actually something that, if you understand arrays, it is a pretty simple operation between two parallel arrays. So the dot product is the sum of products of corresponding elements between two arrays. All right? So as an example, if I have an array, let's say x is equal to, say maybe x is equal to, let's say 1, 2, 3, 4, and then y is equal to 0, negative 2, 4, 10. Then the dot product would just be x0 times y0 plus x1 times y1. You see the pattern here, plus x2 times y2 plus x3 times y3, which here ends up being 1 times 0 plus 2 times negative 2 plus 3 times 4 plus 4 times 10. Now, I'm not going to do that arithmetic in my head. Probably should, but I'm not going to. Let's actually write a little bit of code to do this instead. So let me move this down into code here. And what I'm going to do is, oh, that was interesting. It formatted these in a weird way. Okay, so I can do this with a loop, right? This would be like a 173 exercise. So I'm going to define an accumulator variable. I'll call it dot prod here. And I'm going to loop through each of these arrays. They have to be the same length. That's kind of crucial here. So I'm assuming that the length of x is the same as length of y. Otherwise, this is not defined. And then I'm going to say, okay, let's accumulate the product of the corresponding two elements in these parallel arrays. So I'll say dot product plus equals x index I times y index I. All right, so let's see what that is. It gives me 48. Cool. Now that's fine, but actually there is a better way to do this using NumPy. We won't even have to use a loop, which is cool, and it means that it'll probably be faster too. So you might have an inkling of what we're going to do, right? We're going to use some element-wise operations. So I would say, if I were just to say x times y here, oh, whoops, these do have to be NumPy arrays in order for this to work properly. Otherwise, this element-wise stuff is not going to work. Okay, so that's important. But anyway, so now that they're NumPy arrays, I can do these element-wise operations. So in this case, I can do, or actually this is technically called broadcasting. So what I'm going to do is multiply each element of x by the corresponding element of y, and this gives me a new array. So here we've got 1 times 0 is 0, 2 times negative 2 is negative 4, 3 times 4 is 12, 4 times 10 is 40. I'm almost there, but the dot product wants me to sum these up. So I'm actually going to say NP, there's a method in NumPy called sum, where I can sum these up, and I see I get the same answer. Actually, and it turns out this is such an important thing that NumPy has its own method for this. So this is the built-in NumPy way. I can actually just say, you guessed it, np.x, y. So I pass it those two parameters, one for each array, and it gives me that. Okay, so that's the tool of a dot product. It's pretty simple, and again, it's something I could probably give as an exercise in 173. But it has some very neat properties. And we're going to see some of these properties in the context of sinusoids. So what I want to do now is create a couple of sinusoids, and I want to sample them and put their samples into arrays. And then I want to do the dot product on those arrays. Okay? And the only exercise that you have to do before class on Friday is try this on a few different examples that I'll have you look at and tell me what you see. And then we'll discuss the pattern in class. Okay, but again, the dot product operates on two arrays of the same length. So what I'm going to do here is create two different, let's start with two different cosines. The first cosine is going to go at a rate of 2 cycles per second. And the second cosine is going to go at a rate of 3 cycles per second. And I will literally space the time samples between 0 and 1 seconds, and I'll make 100 of them. All right, and then I do, before I take the full-on dot product, I do just want to look at the element-wise products of each of these. So I want to look at just, the first part here where I multiply the corresponding elements together. Okay? And so let me now plot this one, and then the element-wise products. And let's have a look at them. So here's the first cosine. It's at 2 hertz, so it goes through 2 cycles over a second. Here's the second cosine. It's 3 hertz. It goes through 3 cycles over a second. And now what I'm showing here is the element-wise product of the two. So if you look at these plots, each sample here is the product of the two samples above it. So the first one is 1. 1 times 1 is 1. But then, let's pick out a different one here. If I were to pick out this sample and this sample, see, that's about 1 there, but this one is about negative 0.5. So if I look down at that, the product is around negative 0.5. Okay? And but we have those products, but then remember, the dot product actually sums them all up. And so we're going to just sum them. But when you look at this, okay, I tried to show pictorially, I colored the ones that are above the x-axis, the ones that are positive, as orange, and the ones that are below the x-axis as blue. And what you can see here, if you look carefully, is actually that the positives cancel out the negatives perfectly, or nearly perfectly numerically. So when I look at the sum here of all of these, I get an incredibly small number, so 4.44 e to the negative 16. What that means is 4.44, so this is scientific notation, 4.44 times 10 to the negative 16th. 10 to the negative 16th is an incredibly small number. So this is basically 0. The only reason it's not 0 is because of rounding error of some of these individual products here, and then their sums. Okay, so that's kind of interesting. If you didn't know more any better, there's no reason to believe that the dot product of these two would be 0, right? It's a bit surprising, but we get this interesting pattern. Does that always happen? Well, I don't know. What if I were to make this have a phase shift? So I'll add something, or I'll do what we're more used to. I'll shift within. Let's say I want to shift this over by maybe 0.2 seconds, the first one. Okay, so I shifted that over a little bit. Huh, still happened. That's interesting. Okay. What if I made them the same frequency? So let's make this 3 hertz and 3 hertz, actually the exact same thing. So it's like saying, okay, I'm going to take the dot product of an array with itself. So look at that. And actually, in this case, I get something that's a lot bigger than 0. And the reason is, you look at this, well, it's the dot product of the thing with itself. There's no way I can get a negative number, because you can never get a negative number by multiplying a number by itself. Smallest number you can get is 0, if that number happens to be 0, right? When you square a number, it's always non-negative. If it's a real number, okay. We'll talk more about complex numbers next week, where that's not true. But, okay, so that was interesting. What about if let's try to do a phase shift, but at the same frequency. Okay, so again, yeah, this time we didn't actually end up, we're not lined up perfectly. So actually we were able to get some negatives here, but overall it summed to something that was not 0. Okay. So what I'm going to have you do next is simply try this on a bunch of different examples and just tell me what you see. All right? And then we're going to talk in class about the patterns you see, and we're going to write some code to automate this process over many different types of sinusoids. All right? So enjoy that, and I hope that you get the same spark that I did when I was younger.